Okay. So now let's talk about reactions of epoxides. Epoxides are far more reactive than normal ethers. Okay. So remember that an epoxide is just a cyclic ether. So let's compare these two carbon epoxides versus an ether here. It turns out that the carbons on an epoxide are far more prone to nucleophilic attack than are the carbons on an ether. And it actually doesn't have anything to do with the electrophilicity of that carbon. It's about the same in both. The difference is this, right? If I had a nucleophile that tried to attack this carbon here, this would be a bad leaving group, this alkoxide ion leaving group. However, this bond here is quite a bit weaker because of the ring strain, right? So that makes it a decent leaving group. So that bond's much more easy to break, making epoxides far more reactive towards strong nucleophiles. So let's take a look at our little chart. Remember, this was first introduced in chapter 7. Talking about strong nucleophiles, that means I'm not talking about these guys over here or these guys over here. It's everything in the middle. These are subject to, these are strong nucleophiles that will react well with sides. Okay, and let's actually update this list a little bit. In addition, over here, we now have also our Grignards, as well as the acetylide ions. Those are also strong nucleophiles, strong bases. Okay. And actually, one other caveat is, although these sort of sit in this category, we're going to have a different method for adding a halogen to an epoxide. So I kind of wouldn't consider those to be in the same category right now. All right, the other thing that I would want to add to this list in terms of what would be another strong nucleophile but a weak base be the lithium aluminum hydroxide, right? Those nucleophilic hydrogens. Turns out that these are not good bases, but they are strong nucleophiles, strong nucleophilic hydrogens. Okay, and then we can illustrate this same thing using these reaction coordinate diagrams, so these potential energy diagrams here. If I had an ether and I tried to react it with NaOH, specifically that hydroxide ion, and this is going to try to attack this carbon and kick off this leaving group here. That doesn't really proceed forward because it has this huge energy barrier that it has to climb. But then as soon as I lock that ether into that highly strained three-membered ring, what happens is I raise its energy, right? So an epoxide undergoing the same reaction, it starts up at a much higher energy on our potential energy diagram. And thus it only has this little hill to climb over. All right, and so again, the reactions are going to be, the whole shtick behind these reactions are you have this really electrophilic carbon here. It's nice and electrophilic because it's in this polar bond, but even more so, it's prone to substitution because this oxygen can act as a good leaving group because of that strained three-membered ring. So the first step is going to be the hydroxide playing the role of a nucleophile and attacking that carbon and kicking off that epoxide, that oxygen as acting as a leaving group, right? This is often called ring opening reactions for this exact reason. You can see that you're opening up the ring, relieving that strain of that three-membered ring. That's part of what's driving the reaction. And then I have to follow this up and treat it with water because I need to protonate that alkoxide ion. Okay, so the first step would be nucleophilic attack, where again, that carbon of my epoxide is acting as the electrophile. And then the last step is you got to follow it up with some source of proton, most often water, in a way to protonate that newly charged oxygen leaving group. All right, so this can happen. I mean, this, in the previous slide, we did it with the hydroxide acting as the nucleophile. This could be any generic nucleophile, as long as it's one of those strong nucleophiles, going back to that first page. Any of those will react with an epoxide. So whether it's an alkoxide ion, OR minus, I will get substitution. And again, notice what's going to happen. This is going to be a pattern that we see. I'm going to have substitution on this carbon here, which means that my neighboring carbon is what's going to get the alcohol group, right? This carbon got the alcohol group because I substituted on this carbon here. I could use the cyanide nucleophile. Again, same idea. And again, notice the position of my two functional groups. So what we're going to see are using epoxides are a great way to create molecules when we want those two functional groups located right next to each other. The sulfide ion was another good nucleophile. Of course, what do we call this? This is our Grignard. And remember, Grignards are kind of special because you're not just creating a new functional group, you're actually creating a new carbon. Importantly, though, again, notice the relative position of where that new carbon-carbon bond is and where that alcohol group, that newly formed alcohol group is. And then if I use lithium aluminum hydroxide, what's playing the role of the nucleophile? I have this hydrogen, nucleophilic hydrogen. So that's going to be playing the role of the nucleophile attacking that epoxide. Okay. Regioselectivity. Okay, so because it's all about nucleophilic attack on these carbons, it's always going to occur, it's going to be an SN2 style ring opening, and it's going to occur on the least sterically hindered carbon. So these are going to be regioselective ring opening reactions where the less sterically hindered position is what's going to get the new nucleophile, right? So this gets the new nucleophile, which means that the more sterically hindered carbon is what's going to get the OH group. Okay. Not only that, but there's stereoselectivity because it's an SN2. Remember, SN2 reactions are characterized by an inversion in the stereochemistry. The nucleophile has to attack from the backside and is then inverting the stereochemistry, right? So here, notice that my epoxide is pointing out of the page. Well, when that nucleophile attacks, it's going to attack from the backside. So now my alcohol group and my new functional group, whatever that nucleophile is, they're going to be on opposite sides of one another. Okay, and again, this just goes back to SN2 and the stereoselectivity of SN2 reactions. There's always that inversion in stereochemistry that we see. Okay, now we have another set of reactions with epoxide. So that was taking an epoxide and reacting it with any strong nucleophile. I told you that we had a different sort of category for when we wanted to use those halohydrin acids, not halohydrin, hydrohalogen acids. So for example, HCl or HBr. And so these are going to be acid-catalyzed ring openings. So what do we think the first step is going to be in this acid-catalyzed event? Same as with what we saw with ethers, which is the oxygen is going to play the role of a base, accepting this proton, and then that's going to break that bond there. So this is going to be a proton transfer to that oxygen in the epoxide. Now, if it wasn't a good leaving group before, I mean, it was a good leaving group before, now it's even better, right? So that means, so now I can have my halogen come and attack that electrophilic carbon, and that'll break that leaving group bond right there. Okay, so this is again, an SN2 style reaction. And then I have my halogen located one carbon away from my alcohol group. You could do this in the presence of alcohol, and those will be now playing the role of the nucleophile in the second step. So acid catalyzed in the presence of water. I will then have my just another alcohol group. So this is a way of forming a diol. We actually kind of saw this already. But now if I wanted to instead create or rather, instead of having water include an alcohol, I would just have addition of my alcohol on that second carbon. Right. So again, notice that Your oxygens or your hydroxide groups of your alcohol are on one carbon, and your newly formed functional group is on the other carbon. Reaction mechanisms for this. Okay, so this is, I actually think that if you guys paused and went through, you would be able to do this all on your own with what we've learned about reaction mechanisms at this point, but let's just go through and make sure. So again, what do we think? Oh, come on. What do we think the first step is going to be? Hopefully everybody said proton transfer. That oxygen is going to come and grab that hydrogen of my acid. Now I have this protonated oxygen, which is going to be a great leaving group. So water can come act as the nucleophile, kick. So now I'm left with this type of product here. And then what do I have to do? I got to get rid of one of those hydrogens. So another water molecule will act as a base and receive that extra proton, right? Analogous reaction mechanism for if you had it in the presence of some sort of an alcohol. Okay, so now let's talk about stereochemical regioselectivity of these acid catalyzed ring openings. Okay, so just like we saw with the with just taking an epoxide and treating it with a strong nucleophile, in those cases it's an SN2 type reaction, and so the less sterically hindered is going to be the most favored. Right, so the same thing we see when we're comparing a primary versus a secondary carbon. The primary is going to win. We're going to get nucleophilic attack on that primary carbon because it's just less sterically hindered. However, if there's a tertiary carbon present, we actually will have substitution on that tertiary carbon. Okay, so this might be a little weird. It is definitely more sterically hindered, so this is a little counterintuitive. Although it is sterically hindered, that's not the dominant effect here. It turns out that there's an electronic contribution from the fact that this is a tertiary carbon. It can sustain a partial positive charge much better. We know tertiary carbocations are more stable. And because of that, it actually makes this tertiary carbon oxygen bond quite a bit weaker than the other bond. Okay, so just like because tertiary carbocations are more stable, here we have this partial positive charge that occurs on this carbon because it's tertiary and then weakens that carbon oxygen bond. So when we're comparing a primary versus a secondary carbon, the primary wins because it's more because it's less sterically hindered. When we're comparing a primary versus tertiary though, it's the tertiary that gets substituted. And that's because the dominant factor here is that electronic effect. Okay. Nonetheless, in this ring opening, you will still see this inversion in the stereochemistry, even if it's a tertiary carbon. Okay, so we're not used to seeing inversions in stereochemistry for tertiary carbons. Here you still will, and it's because of the nature of that epoxide bond. The only way that you can have any sort of nucleophilic attack is going to be from the opposite side of where that epoxide is located. And so notice in this case here, it's an acid catalyzed ring opening. This carbon here is a secondary compared to this carbon here, which is tertiary. The tertiary wins. And because of that, I'm going to see the backside attack, and notice what happens to the position of the methyl group. In my reactant side, it's on the opposite side of that epoxide. Once it gets attacked by the nucleophile, it flips or inverts and is now located on the same side as that alcohol group, that newly formed alcohol group, right? So there's this inversion of stereochemistry about that carbon. All right, so just to summarize here, first thing we talk about is mechanism. You should know the mechanism for both of these reactions here. Okay, we went over them. The top is just SN2 type mechanism. This is actually an SN2 type mechanism as well. Okay, you just have your nucleophilic nucleophile attacking. For the acid catalyzed, remember you have to first protonate that epoxide group. So there's that proton transfer to that oxygen. Similarly, in the strong nucleophile case, the last step is a proton transfer. You have to protonate that alkoxide leaving group. Oh, oops. Not that it really matters, but this is supposed to be green. The regioselectivity. Yes, so both of these have regioselectivity, always less sterically hindered. Will be substituted. And this is in contrast to the acid catalyzed, where the two possibilities are sort of diagrammed for you out here. If it's primary versus secondary, the primary wins. However, if there's a tertiary carbon, the tertiary will win. And in terms of stereoselectivity, because these are SN2s, you will always have inversion of your stereochem. Okay.